Hi, I'm Josh Maynard, and this is my solar and alternative energy systems project on hydropower. The first part is on a hydropower research paper, and the second part is on a personal hydropower system. So, introduction to the paper. This is just kind of the general layout of how the research paper is written. So, the first part is they talk about emerging control technologies to stabilize the flow in hydropower. The next part is instabilities in Francis turbines. The next is the digitalization of hydropower. Next are hydro generators with current controlled rotors. Then variable speed hydropower, new concepts in hydroelectric storage, novel technologies in small scale hydropower, and fish friendly hydropower. So, like I said, the first thing they talk about is the emerging technologies to stabilize flow. So, these technologies are broken down into three groups: passive control methods, active control methods, and magnetorheological control techniques. So, the passive techniques do not require external power, while the active ones do. So, the goal of all the techniques that are listed here is to diminish the draft tube surge. So the draft tube surge is the main reason why flow becomes unstable in these hydropower systems. So the there is one main disadvantage to all of the passive control methods, which is that they introduce hydraulic losses, and they also are only effective on a limited number of applications, so they could not be implemented everywhere. So then down to the active control methods, the air injections disadvantage is that at certain operating points it can destabilize the flow. So basically, at certain operating points, it can um, defeat the purpose of what it's trying to do. But at most operating points, it does stabilize the flow. So all the various types of water injection have the same issue, as which that is that they will cause volumetric losses. So there is a loss in energy production there, but it causes a reduction in wear on the dam. So there's a cost benefit analysis that's done there to see if it is worth it to install these systems. And the two-phase air water injection does not yet have any known disadvantages. So besides the cost to install it, obviously. And then the magnetorheological control techniques, it is a brake that slows down the swirling flow. So again, there's no disadvantages identified yet besides the initial cost of installing it. Okay, the next part is instabilities in Francis turbines. So the main reason why this is studied is because the instabilities have an effect on the turbine lifetime. So one of the main problems affecting the turbines is the water structure interaction, right? Fluid structure interaction. So the first example is the rotor stator interaction, which this often causes premature fatigue cracks. So there's a certain lifespan on these turbines, and with some of this rotor stator interaction that creates pressure pulsations and creates cracks in the turbines. So the reason that a lot of these pulsations happen is because the runner natural frequency becomes close to the rotor stator frequency. So this could be fixed by a damping device being put in, but again, that's um, costs quite a lot of money. So another issue here is the transient operating conditions. So if you think of something like your car, right? When you start your car, that normally it has a wear effect there, right? Compared to just if you're cruising 55 down the highway. So it's similar to that, right? When your startup, or you're just running a low load, or you're kind of something like that on these hydropower systems, it creates extra wear. So that's another thing that there causes instability in the Francis turbines. So the next thing here is the digitalization of hydropower. So a lot of these dams and hydropower plants are extremely outdated. So the digitalization here can be applied just by, simple upgrades and stuff like that. So it's been proven that digitalization could increase energy production by 42 terawatt hours, which is equal to $5 billion in energy production savings. So that's something they said in the article here. That's obviously that's a lot of energy production savings. But again, if you think about how many hydropower systems there are around the world, this digitalization of the hydropower systems would be quite expensive. So another thing they like to do here with the digitalization is give a prediction of the lifetime of the dams, what's going to break on them, and just the monitoring of what condition these hydropower systems are in. So again, that's just kind of a to stop issues before they start type of thing. So the next thing I talked about is current controlled rotors. So large scale hydropower plants have vibration, temperature, voltage, and current sensors that are already installed there. So those are just used for protection methods at this point, right? So if the vibration gets too high, temperature gets too high, voltage or current get too high, it shuts down the hydropower plants. But these same sensors could be implemented to counteract the vibrations. So there's already a split rotor systems that each pole is used as an actuator. So you could apply these, you could use the sensors to control those actuators, and it would then cause, or it would allow you to stop the vibration and stuff instead of just using it as protection. So that's with these current controlled rotors, that's kind of, again, that just goes back to trying to reduce wear, right? So reduce unwanted forces on the generator, which is reducing wear. So variable speed hydropower, you have two systems here: the converter fed synchronous machine and the doubly fed induction machine. So converter fed synchronous machine uses a frequency converter to control the speed and voltage of a synchronous machine. Doubly fed induction machine has a wound rotor induction generator where the rotor circuit is fed through a power converter, allowing for independent control of rotor speed and reactive power. So both of these options make it so that hydropower plants become more efficient at all points. So again, this would be a very good thing for just efficiency and energy production because it does make them more efficient at all points. But these have been installed in some cases, but in many cases the cost of these outweigh the benefits. So that's why this is not something that's going on at a large rate. The next thing here is new concepts in hydroelectric storage. So the first two here are basically just flywheel energy storage system and supercapacitors plants along with hydropower plants. So it basically is just combining other electricity producing or energy producing areas with these hydropower plants. So flywheel energy storage system combines wind and hydropower energy, and then the supercapacitor plants can be combined with the higher hydropower plants. So the supercapacitor provides a virtual inertial response, whereas the hydropower provides frequency regulation, which makes them a good pairing. So then there's these underwater pumped hydro energy storage. So this is where like the top there's a reservoir here, and the top reservoir is the like the river, and the bottom there's a bottom reservoir that's built in. So to do this though, you need to use a vent line or a smaller feed pump. So the vent line is needed to stop pressure variations inside of the bottom capsule. So that can also be done with a smaller feed pump, but it's more cost effective to just use a vent line. Okay, the next thing is technologies in small scale hydropower. So the reason why this is such a big thing now is because large scale hydropower plant implementation is difficult due to environmental impacts. So you have gravity hydraulic machines, which are hydrodynamic screws and gravity water wheels. These are things that I'm sure all of you have saw, like old sawmills and stuff like that. They use these water wheels. So they've been experimenting with using pumps as turbines, which you can just reverse a pump and then use it as a turbine. Also, there's a lot of these rural small-scale dams that are currently used for irrigation or flood mitigation. So these could be upgraded and added on to just create energy without having an adverse environmental effect. Okay, the next thing here is fish-friendly hydropower. So you could, they've been creating fish passages here, fish ladders that allow the fish to not be stopped by the dams, right? This reduces the overall efficiency of the dam, though, so that's why this is kind of a give and take here. The Alden turbine design, it has 3 blades with a slower rotation speed, so this would hopefully allow the fish to not get caught up in there, right? And then minimum gap runner design reduces the gap between the runner blade and the hub. Another thing, just preventing fish from getting caught up in there. So, okay, so the next portion of this is the micro hydropower. You know, that's a thing that I researched. So, overview: the micro hydropower systems are small scale power systems that convert the water flow into electrical energy. This is normally done using a turbine that is spun by the water and hooked up to a generator. So I kind of spoke of this briefly before within the article. So the first thing to know about these small scale systems is the power calculation. So you have the gross head, which is the vertical distance the water is falling in feet. Then the net head, which is the gross head minus the losses due to the friction or turbulence in the piping. Then the flow, which is the quantity of water, right? That's pretty self-explanatory. So to calculate the power output, you multiply the net head by the flow, and then you divide that value by 10 for the losses, and then that gives you the power in watts. So then once you get this power output, you need to obviously do a kind of an economic breakdown here of, hey, is this something that I want to install, or is it effective for me, or will it take forever for the benefits, the savings to outweigh the initial cost. So you have some different turbine types here. Impulse turbines, they rely on the velocity of the water to move the turbine wheel. So you got 3 different types here. The Pelton wheel, that's where water's funneled into a pressurized tunnel with a small nozzle at the end. The water strikes the buckets on the wheel and create a force that rotates the wheel. Got the Turgo impulse wheel. The Turgo impulse wheel uses the same concept, but it's more efficient because it has 3 nozzles that go out and hits all the buckets at once. You got the reaction turbines, which, you got the Jackrabbit turbine, which is like a small propeller system. So that's ideal for areas with small or no head. That's really the only areas those are used in. So then the second type of turbine is the reaction turbine, which relies on the pressure of the water to turn them. So these are similar to like a boat propeller, but all the blades are set at different pitches, so it allows it to spin easier. So, okay, so you have one element here, the pumps and water wheels that can be used in place of turbines, right? So like I said before, you can use a pump as an alternative to a turbine because they're more readily available, right? You can just go buy a pump, so it can be run in reverse and it will act like a turbine. So, like I said before, too, water wheels. I think everyone should have saw them. Like old sawmills or something like that. Just water wheels turn, and then it can turn a generator, right? But those take up a lot of space compared to a turbine or a pump, so that's the disadvantage of those. Next, you got the next part of the system, which is the generator. So, obviously you don't just want to spin the turbine or the pump or the water wheel, right? You need to hook it to something. So you hook it up to a generator, which creates DC electricity. In many of these micro hydropower systems, a kit's sold that incorporates all that together in an enclosure, right? So, not many people want to just use the DC. So then you put a transformer in there also to change the DC electricity to AC for use for, in the home or whatever you want to use that for. And then there's my last page, which is just all the references. So thank you guys for listening.